Well, welcome everybody to sessions 22 and 23, where we have an opportunity to discuss failure criteria. And we've already discussed the importance of the yield strength of materials and the shear strength of materials. And those quantities are very useful for cases where you have uniaxial loading, right? So that you only care about a stress in a normal direction, or you only care about pure shear for shear strength. And we've talked about combined loading, we've used more circle, and we've been able to figure out how to think of equivalent states of stress for a given state of loading. And so today we have the opportunity to learn about how we link the material properties of yield strength and shear strength indirectly to whether or not a structure under a given loading is going to fail. So as you go through the material, the first, this should be session 22. The first thing that you'll get to do is review a little bit about material testing. And we talked about this before. We had a session on material properties. And then we'll go into how we can use a criterion for maximum normal stress with brittle materials. And then the third part is how we use a criterion for maximum shear stress for ductile materials. Okay, so session 22 is going to talk about material testing. Okay, and we're going to talk about max normal stress. And this is a criterion for brittle materials. And also max shear stress. Okay, and this is a criterion for ductile materials. And as a review, what are some of your favorite brittle materials? Favorite brittle materials?
Glass.
Yeah, glass is a good one.
Ceramic.
Ceramics. Yes, these are brittle materials. Even some iron-based materials can be thought of as brittle. Okay. I'm trying to think of brittle foods. Like,
Crackers?
huh?
Crackers?
Yeah, crackers are pretty brittle until they get soggy, right? A lot of the hard candies, those shatter.
Bread if you cook it too much.
Okay, yeah, bread I'd say often it has like a really interesting.
Or char the bread.
Yeah, well, it's interesting, right? Because you want it to be kind of in between sometimes, right?
Yeah.
You want it to have this nice crispy exterior, which is brittle, with a nice ductile inner parts. For many types of bread. I mean, there are other types of bread where no, it's like, you want it to be kind of more brittle. I don't know if roti is considered a bread or not, but that's pretty brittle, right? But the naan is usually a lot more ductile. And then you think about French bread, which has that nice crispy on the outside, ductile on the middle. You think about sourdough bread, kind of similar, usually a little bit crispy on the outside and nice and soft on the inside. You think about Yeah, all kinds of different breads. The breads that are leavened, breads that aren't leavened. Okay, I'm glad you brought that up. Sorry, Ethan, I'm glad you brought that up. That was an interesting tangent for me, at least. Okay, so I'm trying to think of how you can remember that maximum shear stress is a criterion for ductile materials and how maximum normal stress is a criterion for brittle materials. Any suggestions for mnemonic here?
The way you mean it's criteria, do you mean like that's where it would break it, or that's like the force it's strong against?
Okay, so what we mean is which, right, we have normal stresses and we have shear stresses, right? And we know now how to go between both types, because we have more circle, we have our stress transformation equations. And so what we're talking about here is you look at what the maximum normal stress is to determine whether it's going to fail or not, right? For example, you can have a material under pure shear, right? And we calculate out the tau. We calculate out the shear stress, right? But in pure shear, how much normal stress do we have? Zero, at least in that particular orientation, right? So now, if it is a brittle material and it actually fails because of normal stress, we had to orient that material 45 degrees, right? Or we had to look at the element 45 degrees to figure out what the normal stress is, right? For pure shear, yes, that means that so we're talking about pure shear, right? So in pure shear, the Mohr circle looks something like this, right? This is where we're saying this is sigma, this is tau. And so if I'm in a state of pure shear, I'm like here and here, okay? No normal stress. And so the R, right, the tau max that I have is just equal to R. And if I need to look at the equivalent normal stress right here, so this would be sigma 1, this could be sigma 2. Sigma 1 is going to be equal to R, right? So that's a nice case, but you're going to be calculating out this, from a TC and J perspective, right? And then we have to think about what's the equivalent normal stress. And this reminds me of a classic example, which I forgot. Normally I'm a better person when it comes to, yes, you know what I'm talking about, right? Have you seen this before? Do you know what I'm going to do with this?
Oh yeah,
No. Okay, so what we have here is a simple piece of chalk. And this piece of chalk is a rod or a shaft that we can load under pure shear. Now, what did we just say? When you have pure shear, right? If you have a rod, okay, and it's under pure shear, let's say we're twisting this direction, well, that's hard to see. Okay, so that's a tau app, right? And I've got to have a tau app in the opposite direction up here, right? T and T, in order for it to not break. So we just said that this element, let's say where's the stress going to be the highest? The stress is going to be the highest on the outside, right? Because that's T, C, and J. And we just said that the shear stress, okay, is what we see. But we have an equivalent normal stress at 45 degrees, okay? So now, if I put this under shear, where or how do I expect it to fail? I expect it to fail. This is, now I should say chalk. This is this is a brittle material, right? This is a brittle material. So I just said that the maximum normal stress criterion is why this would fail. So this means that when I apply pure shear, I expect that normal stress dominates, and the normal stress is 45 degrees, right? So this is the, if I were thinking this is the shear that I have, right? Okay, I've got to orient it 45 degrees so that I get an equivalent. This is at the same location, mind you, right? But this is why I dominate. This is how it dominates. So it's going to want to fail along this plane, 45 degrees relative to what the shear is. Okay, so now, what will that look like? Well, we can actually see it. This is a classic example, right? So we take a piece of chalk and we twist it. Look at this. Look at this. All right, you can see I twisted it and it failed. All right, see this? It failed in a helical fashion at 45 degrees. Okay? 45 degrees. All right? So this is an example of a brittle material. So take a piece of chalk and go ahead and twist it. Okay? And see if you can get it. That was a little bit too small of a piece of chalk. Let's see. Did it work? Did you get 45 degrees?
Yeah, like
Kind of? Sort of? Ah, yes. Ethan, here's a nice big piece for you. Oh yeah, you got it. All right. Now, yeah, you got 45 degrees. Everyone's getting 45 degrees, right? So, if I take this material, okay, and the next person's probably going to be upset because we're breaking all the chalk in the room, okay? You got more chalk? Yeah, that's right. You got more. We'll have to put more. Okay, so you just saw how we broke, right? We twisted it and it fractured at 45 degrees, as we predict for this normal criterion, all right, for a brittle material. What happens if I put a bending moment on it?
It would snap.
Yeah, and what's the angle? It should just snap, right? And we should see a pretty good fracture. Now, the top, if I bend this way, right, that's putting a negative moment on the beam, then I expect the top to be in tension and the bottom to be in compression, right? Still a normal stress. Now, brittle materials are often stronger. They have a higher strength in compression than tension. So if we had a really fast camera, I would expect that we'd see the top, if I bend this way, see the top break first, right? And then a crack propagate, right? But this is I don't have a really fast camera, right? So let's see what happens. I'm now going to apply a bending moment. Look at that. That is 90 degrees. That is really orthogonal, okay? All right, yeah, so you guys can see it, right? This is super exciting, right? Super exciting stuff. Okay, and Jason, you missed the twisting, but you can try to twist this and see what happens.
Small piece?
Yeah, try twisting a small piece. Twist. Whoa. Okay, you can kind of. No, sorry, you just made a mess. Sorry about that. Let me give you a bigger piece if I can find one. Yes. Look, I found a huge one. Okay. Whoops, I discouraged him so much that here, take this one and twist. See what happens.
Yeah, there you go.
This one will be so
that's a
awesome.
different elastic model.
Twist. See,
Oh.
45 degrees.
Fancy.
All right. All right. Okay. So that is an example of what happens with brittle material. Okay, now what happens with a ductile material is that ductile material it's not as obvious, okay, I guess, because what happens, well, I guess it can depend on the material, right? but the material is usually, at least in a tensile test, okay, it's usually loaded uniaxially, right? And if you look in Hibbler and you look online, it's complicated, but what actually, so you know, the element, right, is just experiencing stress like this, and the maximum shear stress is going to be at 45 degrees, right? That's where we get a nice little shear stress. Okay, like that. And so what you'll actually see, or what you'll see in some materials, is this failure along these slip lines that are 45 degrees. Those are sometimes called Luda lines, okay? And that's for your ductile materials. So I don't have a really good mnemonic here. I mean, steels are often considered to be ductile, okay? A lot of them are. So maybe steel is like shear, so shear steel, I don't know. But the brittle materials are going to fail in normal criterion. All right, how many times do we repeat that? I don't know. That's good for enough for now. Okay, so what you'll see as you go through the videos is that there's a new plot that we use to chart out whether or not something is going to fail. We already have our Moore circles, so we have the ability to kind of look at, you know, what the shear strength or shear stress and sigma are, and what that how they related to each other. In this case, what we have are sigma 1, sigma 2 plots, okay? And these sigma 1, sigma 2 plots are going to be not for x and y, okay, but for principal stresses, okay? So what you can do is you can figure out what the state of principal stress is, what your principal stresses are, and then plot them to see whether or not you're in this geometry. If you're outside this geometry, okay, then you have failure. This particular geometry, this is for maximum shear stress. This particular geometry is for maximum normal stress, okay? Again, go through the slides. So go ahead and start going through things, and then in a little bit, we'll come back and we'll talk about another criterion for brittle materials, another criterion for ductile materials, and safety factors. All right, so go ahead, get started. And then if you are still working on session 21, that's fine. I can go around and I can answer questions on that. Okay, let's see here. Yep, all right, good. And no, I haven't graded the exams yet. Okay. My goal though is Monday, because the final exam is a week from today. Oh, yeah. The class is gonna be over in a week, guys. Yeah. Rapid fire. This is my first time teaching it in the summer, and I've never gone through the material this fast. So it's intense.
So how many sessions do we have? Like 3 more?
25, right.
25?
So we have 20, no, we have 2 more, because we have 22, 23, and then 2 more on beams. We do deflection on beams, which we haven't covered, which is a very important topic. And we also do some superposition and indeterminacy again. So more constraints than we have equations, or more unknowns than we have equations, and more constraints than you would have in a statically determinate system.
Is there like a lot of new stuff, or is it just like combining?
The beam bending stuff will be pretty new.
Okay.
That will be pretty new, and we'll get into that on Monday. And then Tuesday, we do the indeterminacy, which is another thing. And then Wednesday is a day off, or a day to review, answer questions, and then Thursday is the final. Okay. Yeah, so really fast, really fast. I didn't see that there was a break for the 4th of July. I understand it's a holiday that we celebrate. Yeah, so I don't know what to say about that. But the 4th of July, enjoy hopefully you can enjoy a picnic or something in the afternoon or evening, and fireworks.
You find the stress of the fireworks with lighting.
Right. Yes. Well, the canister or the
Yes.
container is
Those are the
failing.
giant ones.
Yes, it fails pretty catastrophically.
Well, let's get one of the giant ones and just do color demonstrations.
Color demonstrations.
Yeah.
Okay. Yeah. Group trip. Where do you go for fireworks around here? Actually,
I'm not from around here, so.
you're not right. Okay.
Neither of us are
To
from around
like buy fireworks or to like
To watch.
They have a good fireworks show in East Brunswick. In a place called Heavenly Farms,
Okay.
and they also have a huge thing in Milltown.
I have been to the Milltown one.
You have?
Yes, it is huge.
It is really big.
I agree.
That was cool. I like that one.
Okay. Yeah. Yeah, we took that. I took the kids a couple years ago.
Yeah.
We were.
They have it by that gas station, by the ice cream place. Ice cream depot.
Ice Cream Depot is really good.
Yeah, it's like a famous like ice cream place around here.
Oh wow! All right, so I have. Even though I'm not from New Jersey, I feel like I've experienced some New Jerseyan things. Great. Let's see.
So you're not from New Jersey?
I'm not. I'm from Florida originally.
Oh, yeah, they thought.
All right, let's go on. For those of you that came in a little late, we had a little demonstration of real materials. You twist that, twist it, you'll see that it breaks in a very interesting way. Let me get you one more too. Yeah, so you can take a piece of chalk and you twist it. Okay. And what you should see when you twist it, it feels something like this. Yeah, you did it. You got it. Okay, you made a mess. You did it. You did it. See, so you see how it has like it fails at 45 degrees. Okay? And the reason it fails at 45 degrees is because, oh yeah, good, you got a good twist too. Oh, I'm sorry. Okay, whoops. Yeah, so I should warn, you don't want to introduce dust particles to your electronics. Right, so that 45 degrees is associated with the fact that it's a brittle material and it fails through the maximum normal stress criterion. So we're putting pure shear on it, okay? And so the shear, right, is going to be orthogonal to the material as you see here, right? So you have the shear stress, right? But then you have to rotate 45 degrees and then it fails on that normal. It fails on the 45 at 45 degrees because normal stress is what dominates the failure of brittle materials. So that's all. I'm gonna go around to all the classrooms and great chalk. You can put the chalk on the chalkboards, or I can take it too. Yeah. Thanks. Anyone else have chalk that
I
they want
still
to?
have few usable pieces.
Huh?
I still have few usable pieces.
Yeah, exactly. There's still plenty. Ooh, that you can combine it. So nicely. And then we also did the example of if you put it under bending. Well, Mark's not here, but if you put it under bending and you snap it, it snaps really nicely normally. So if you bend it, Mark, it also snaps it really nicely right across. Yeah, like that. Just because it puts. You want to do that one too, or you just wash your hands? You just wash your hands. So you have to watch. Okay. Because that's bending stress. of the reasons why we are doing this topic, or we have both of these sessions today, is because it's the weekend. Because it's a lot. It's a lot to absorb. There are a lot of questions too. Yes, Jason.
Will the final have like an emphasis on the last like 5 sessions after the second exam, or will it just be evenly distributed?
It will probably have more emphasis on the last 2 topics.
Yeah.
Partly because we don't have the 3-hour block that you normally have for the final exam.
The final's still gonna be just the 2 hours of
That's right, because we didn't schedule. So I don't, if I had scheduled it at the beginning and said, look, it's be 3 hours at the end, then I think it would have been okay, but I didn't do that, so it's, it's just gonna be short. So it'll be short, like if you look at previous final exams, they're longer. Oh, this will probably be somewhere between.
Yes, we have this and we have this and we have that.
I think the team like you were talking about.
Well, the whole, it's still super impressive, it's real fire. This, that one thing was strange, was like, I were 2 minus the 3 minus well. This stuff. It might have.
Yes, Mike. What's up? Which one?
It's last night's assignments.
Yeah. Yes.
Is B gauge just like the magnitude of all the microstructures?
So it's the B gauge, right? Is looking at the A, B, and C, right? And this is a 45. We're using rectangular rosette.
You know, rising strength.
Rectangular rosette
I know strength.
with an A gauge, so it's the A sensor. The B sensor's at 45 degrees, and the C is 90. So if you look, and right there's an epsilon A, epsilon B, epsilon C. That's that you expect. So it's not that hard of a problem, really.
Oh, that's from.
It's down.
Well,
It's down.
it's whatever, this
It
was
actually is up,
5 or 2.
Oh, right there, oh.
Yeah. right? So this is saying, look, for a given general state of stress, right? We know how to do transformations now, right? For stress, but we also know how to do them for strain, right? So it's like, okay, I have some state of stress, and we're saying that they're really all at one point. We're assuming that they're close enough that they're all at one location. So then, this is, in that direction, where they align along with the x. The b is 45 degrees to it, and this is at c. So it's just like, oh, if I wanted the sigma, or if I wanted epsilon x, right? Then that's what that gauge gives me. If I want the epsilon y, that's what that gives me. And now I don't know exactly how to figure out what the shear strain is, so I need a third measure. And then I use that one for that. Or I use the combination of all 3. Sometimes, we'll mix. I'll mix the word strain gauge and strain rosette. A strain rosette really emphasizes the fact that there are multiple strain gauges in a particular pattern.
trying to raise it, just gives you reason there. We do the same, cosine ninety easier than so. Start first part. Yeah, so it's just his first part. Interesting last time. In here, you divide by 2 and 90.
Well, just
Work to make it
multiply both sides.
Actually, 8, yeah.
So it's E1 minus EX.
It's not that. Because then minus 6.
It's E1 minus EX.
Any questions? Very quiet.
That's it, these two, it's multiplied by two, yeah. And then just like factor out two for this, so it's just negative EX plus Y sine 90 comes in. One. We split it up here. Cause I got like times whole number.
minus
No, it's negative EX plus EY times sine 90.
sine of b is 1.
Yeah. So you have negative EX.
And I did
Yes, minus.
I did ey minus.
So we see, so you move, it's double net of EY.
Exactly.
That
Yes.
times 1 times 1E6 is you're converting like that. So times 1 times E6 power 4 is 0.
6. No, 40. That's what I was asking.
And then that negative.
Yeah, I spent it, I was just messing with the units. I thought I already hit it with us.
Well, they already converted it.
Yeah, I thought
That's why I said here, this way like times 7 negative 6. The principal strength is right. Right, that's principal strength.
Yeah.
Okay. Let's open that.
Let's actually not take, I guess, the angle to the principal strength.
Yeah. Everything for that. Especially this.
Let's see, so that's little.
Yeah, this is the strength, just like plus or minus the radius.
That's the principal strength thing.
As you. Oh, large, okay, so we just positive that, right?
That's probably.
Yeah, so just add that. instead of doing all that, you can just type like 5 names. Yeah, so the X is a great trick. X is this one. It's a very good thing. One of the question 3 is the 2 is whatever you put there. That was that. It's supposed to. 2 you're fine. That's what it is.
Was it at least 1 month?
Yeah, it was like 3. So you get
Nine times 10 to the 6, right?
10 to the power. Yeah. Also, I'm going to do more sort of those straights that.
So is anyone going surfing?
After our final.
I think it's not bad today. It's not great, but it's not bad. Don't worry, I'm not broadcasting this on YouTube. I thought I have a lot going on at home, and I was like, oh, maybe I should try to go surfing before class tomorrow. But it became evident that was a bad idea. There's a lot of stuff going on. It's like I can't just take off. But yeah, this is it's
the beach from here?
huh?
How far is the beach from here?
This is about
That's like
55 minutes.
yeah, because I live in like Swan. Like that was the beach I got every day.
Yeah, that's this webcam.
I
is
didn't know
free.
they had one.
They do. This one is, I mean, Surfline and some other websites have, you know, but like this one is like nonstop, and you can see it. And it gives you a pretty good idea. This is one of the hottest spots for
It was always
surfing.
so crowded.
Yeah, it's one of the hottest spots for surfing in New Jersey.
That was much more helpful than using magic seaweed.
Then using what?
Than using magic seaweed.
Oh, magic seaweed. Yeah, I'm not. Oh, I guess I gotta be careful what I say. So this is the one they can't see this. This is the one that I use, and it's free, and it's not bad. Okay. All right. That's the website. So
Surf forecast.
yeah, and it gives you up to 12 days in advance.
Does
So
it tend to be pretty accurate?
this is pretty good. So like yeah, so I check this one in one of the main sites that we talked that was mentioned, Surfline, and so Surfline. Anyway, whatever. I don't know why I should hold back, but yeah. So, but yep. And it doesn't look like it'll be. I mean, for me, 4 foot happiness. All right. After 4 foot, that's when it starts to get a little dicey for me. Like,
If it's the
yeah.
if it's the East Coast, we get over 4 foot waves, they're most likely gonna rip your head off if you get
5 and well, I mean, I feel like there's some really good like Manasquan, Belmar, a lot of different places. Like if you know what you're doing, they're ripping.
Oh, yeah, no, it's
They're
great.
ripping.
I'm just saying, like, the water on this coast is pretty, but as soon as it starts getting above like 4 or 5, the way the water breaks.
Yeah.
It's,
It's
5 foot wave here is, you have to know what you're doing. You have to
Yes.
be anywhere near that wave. Not
Well,
even-
6. I think 5 foot. Yeah, you had to like. I can handle 5 feet if it's not too fast. Yes, here, but but I'm also really out of shape and my shoulder is still recovering. So now I definitely went. But this morning I was like 3 feet like this. I was like, oh,
That would be perfect.
right. This is like good for recovery.
I think I've asked this, I forget, do you use a longboard or a shortboard?
So I have a 6'1", a 6'3", and then 8 foot.
I tend to use, I think, a 5'10",
Okay, yeah, that's
or I have a 5'6",
uh-huh.
and then I have a 10 foot.
Okay.
So
Oh,
it's
yeah.
Quite.
So that's you have yeah. So yeah, the lowest volume I have is probably around 33 liters. So the 6'1", but yeah, I don't venture. I had a shorter board that was like maybe around 30, and that was like it just wasn't fun for me because I was like it was fun. Actually, it was fun when I got up. It wasn't. It was just the paddling was intense. You had to be able to paddle.
That's what I started on, so I just think,
Yeah.
I can't use bigger boards very
Wait, a
easily.
10 foot. George! Look at this stuff. Look at these guys. They're having some fun.
What is?
I mean, this is mechanics and materials.
Where's it?
That is.
Oh.
Professor.
Yes.
That was the issue.
Just give me 1 second. Just give me 1
They're
second.
trying to why are you throwing that? They want to start to fight that way. I was thinking, like, let's just raise it, so I tried to both track without dividing. I tried to list it out dividing. There's.
Okay. What's up, Mark?
So I understand like pretty much all of this, but if we were to solve for strain on B, we would need shear strain XY, right?
Gamma XY,
Or
right?
gamma, yeah, and then gamma XY, we can find it by using this.
Yeah.
But then if we equate them both together, it's the same.
Is there engine? Shear strain. This is for X and Y, right?
Yeah.
So for that element, if I'm looking at it, it only says normal stress act.
Find some time for my summer plans.
So it's because it's like a
That was their lower.
pressure.
Right.
So there's,
At least in that particular orientation.
We're still trying to
Okay. And that I'm not saying that you could have stress, right? You'd have shear strain in another orientation, but in that orientation, you don't. Does that make sense?
so if it was like angled like 60 degrees,
Sure, anything, because that's a cylindrical one, right?
Oh, yeah.
So yeah, if you do a rotation, then yes, you expect to have shear strain. But that particular
And the
location,
earth fire was
or at that particular orientation and location, there's not.
so
You just got in the middle of New York and.
Remember, there's a difference between A, B, and C, and X, Y, Z.
Yeah, compared to it, like it's.
I'd like to go past.
So all you need to do is use that. And that's 0.
We can go stuff on the two.
Yeah. Great, looking forward to somewhere in the skydiving, and I want to try surfing.
Yeah, like,
This is that's right. So, I have a chance to go to the beach yet, so.
well, I did before I started.
short of that one.
I wish we were surfing right now, but we're here. Huh? You like the haircut? Thanks. I got my haircut last night. My wife just took the buzzer that I had. Yeah. Like if you get one of those clippers, like for $30, and you use it twice, it essentially pays for itself. And I've had this pair.
Use it once, it pays for itself.
Yeah, depends. Well, it depends on. I don't pay that much for a haircut. No, I mean, yeah, you're right now in today's economy, probably, yes.
It's like $40 a cut.
This?
Where?
Whoa! I mean,
It's safe for me. It's
Women pay like $80 for a haircut.
yes, this
so.
is true. Yes, this is true. It is usually less frequent, though, than men's.
That's
But it's still. So, yeah, so, 20, yeah, like
Weird.
super cuts.
Not super good.
Oh, not super cuts. Oh, okay.
Man has teeth.
Actually,
I got one middle of the blue, it's like, mine's like,
my
that guy I
like
go to, but he's super.
12 years.
Yeah, he likes it.
Well,
I can't, even if he goes up to 60, I can't.
Well, you have style. This is
States.
not much style.
Dude, just like my
Functionality.
My dad too. My dad
Yeah,
he just goes into the bathroom, goes
Yeah.
and calls it a day.
Yeah.
Italian.
That's another way to motivate.
Arabic?
Well, to motivate to get help. So like if I start to cut my hair by myself, and you know what I like do it, and it looks horrible. Like, but I don't take off too much. Like I just do it, like,
Past 10 or so.
and then
Yeah.
it's like, okay, I need to help you. So then. Questions, comments, criticisms? Turn on your Wi-Fi. Wait, what, your Wi-Fi's on already? Really? Yeah. That's a bummer. Yeah, so another evidence of my cheapness. I have 1 gigabyte of data on my cell phone for a month. No, yeah, so
You don't run out.
I've run out like once, so like I'm a little prideful about this. I was like, I had 120 megabytes left, but I had this trip, actually it was the beginning of the semester, or the beginning of the summer, I had to go to California and back. I was like, I think you can make it to and from California on 120 megabytes. I did, because the Uber was a little tricky though, so like I had to like, I had to like out of the Uber, just like shut off the data.
That's great.
How much?
48
gigabytes? Whoa. Well, you know, my computer, like if you look at how much your computer uses in a month, yeah, that's not absurd, right?
Yeah.
But, yeah, so I mean, you just only do, you know,
That can, that too, right?
and email, and occasionally, like, you know, if I'm selling stuff on, or getting rid of stuff, whatever, like, you know, marketplace.
Oh, I love this marketplace.
That is,
Almost my data is podcast and driving.
what's that?
Most of my data is podcast while driving.
Pocket, yeah, well, you can download the podcast before.
You can.
That's what I have to do. I
You
download the
can.
podcast before.
Well,
and then-
problem is if you want to add limited space on it,
Yeah.
then you can do that.
So I have this plan that I can't find anymore, but I think now a couple companies have similar plans. Like it's like $5 a month for a gigabyte. I think now I've seen them for like 6. So once my provider decides that it's done, then I'll have to switch. Yeah, I use it because I don't even have you can do talk and text, I think, through some special thingamabob, but it's really just data. So my talk, I use Google Voice. Alright, sorry, yes, this is not helping you with your homeworks. Huh?
Okay.
Right.
Sounds good. How far away is this place from to? So,
Mark, did that one work? Did it work for you?
Yeah, yeah.
It worked? Hey, how's it going?
Do you know where that is? No, he decided not to come today. Yeah, he texted me this morning, it was like, David.
Got her. And I just sat on my bed to check text and fell asleep. I woke up at 10 o'clock. We're in TV now. He's like, I was like, oh, fine. I get in my car through the third grade plate and someone crashed in the corner there, of course.
But it's these is always in like something.
Dude, whenever I'm like running late.
Yes, we went late, there's some delay or something like that, someone like.
For me, it's
Bro, I thought you just
I'm running late. The universe is like, you know what, I'm gonna be nice to you.
Yeah.
And I'm actually
I was checking that.
No, here's the problem. It's because when I'm supposed to be on time, then they're like, oh, no, you're not. They're like, that's not how this thing works. And they throw everything at me.
I want to track it. I think 76% red lights. I just got tracked it for 2 weeks because I was like, this is ridiculous. 76% of the time I hit fucking red light.
I didn't hear it, there's one dash coming there.
You know what I never get when I really get a text message that I never get.
Oh, yes, exactly, that or you want to check the that's what you never get. The way you get nowhere, just have something important to check your phone when you can't.
Yeah,
Like,
exactly.
always, that's the one. Unless you're late, then those.
We can talk about the exam, right?
No, that's like the.
Wait, no,
announcement.
no,
That's the-
Yes, we can talk about it. What do you want to talk about?
That integral question, yo.
I forgot to do that
1F. Yeah, 1F.
Right, so the integral, right, so you have, f equals dv dx, right? And the tricky thing there was that it's negative because of the convention, right? So you come up with the equation for w, right?
Yeah,
But it's all going downward. So the integral of that thing, right? And that one,
Not gonna let
right,
it.
so the question,
I know the first one is wrong, the second.
I think everything.
Dude, I don't know. I thought you knew it, but I didn't have enough time to check.
Sort of the.
right, so,
The integral must because I wrote the
Right,
integral
so-
with a problem. I don't
what
know.
we're talking about here, right, is this guy.
And it's literally just like a steeper version.
Well, I did that, cause I was like, I'm gonna guess it's cube, cube over 3, so I did that, so I wrote it that way. And then it's-
Okay. So the thing is that this is actually, when you do the integral, right, we have v is equal to integral of w dx, right? What we have to remember is that this is actually negative because it's coming down. So here, right, what I would say is, well, it's first w max, right, and then I have a w max over L times x, right?
Yeah, cube.
But this is actually
I did that, so I.
like this, okay, because it's going down by the convention. So then when you do the integral out, right, you're doing the integral of this guy.
Okay, that's a big reason. Yeah.
Okay. Now the tricky thing here is, so this is going to be you know, you have a C1, right? And the C1, that is going to be equal to what, right? Because remember we had on this beam, we had this is on a beam, right? And we had
Yeah, and then you one got, okay, so it's what do you? Use that.
right? We had these things. So we needed to know the internal shear force just at the left side, right? And then internal shear force on the left side is just equal to RL, right? Because so the V left was equal to RL, and that it should be equal to 1/2 W max L, right? Okay. So the C1 over here is like that. And then you want to check, right? What you want to do is you want to check. So when x is equal to 0, right, then we get v is equal to this. When x is equal to L, right, we need it to come out to be 0. So we plug in x equals L, that's going to be W max, yeah, it's going to be 1/2 W, it's going to be 1/2 W max L. We have this minus W max L, and then we have a plus 1/2 W max L, so it works out. So we've satisfied both boundary conditions. Okay. Well, really? Then we did this. This was okay. I mean,
I didn't think you would ask for the exercise.
it was. We said it was part of the. It was session. It was session 12. It was session 12. Yes.
So I made my integral with x facing the other way so that there wasn't.
You told me when you turned in
Yeah.
your exam. I haven't graded it yet. I'm not sure what I'm going to do.
Because if you go from the, it'll give you the same, it'll give you the right answer.
I'll take a look when I see it. Yes. Yes. All right.
Because all of my integrals are the same, I just don't have the constant
Offset,
for
yeah.
integration.
Yeah. Yeah. It is fair to say that you're going from the right to the left.
Yes.
I look at the wording. I guess I didn't specify to use. Did I specify use the coordinate system or not?
I don't know.
So I'll see what I wrote.
But I realized that there was a coordinate system associated with it with like 2 minutes left. I was like, well, I can't fix this now.
If you forget the negative sign, then your boundary conditions don't work out.
Yeah, I was like, because I was plugging it in the end, I'm like, this doesn't make any sense. Why are my boundary conditions?
That's right, because it's the negative convention.
Oh my god.
Guess who else made that mistake? I was like, why don't my boundary conditions work out? I was like, that's because I messed up the convention. And then I flipped it.
Because I was doing that, and then I was like, alright, like,
That's it's a again, those conventions, they come back to get you.
so I was like, I can't move on. Like, I'm checking my work at this test, and it's just not working. So it's like, either everything in this problem I did is wrong, or this one part is wrong.
Yeah, it was a little one of those things where I'm like, what? Why? And then I was like, oh yeah, I made the same mistake that
But when you actually do
we
that,
could all make.
it goes down to 90-0, so we could ignore that time part, the second part of the equation. So it's just no. I mean, like in the equation, it's e1 minus ex minus y over 2 sine of 90 is 45 degrees plus 1. So that you have.
What did you guys think about the other part though?
Cosine 90 is 0.
Part
So you
B
need
of
to
the
go
left
over
on
this
my
compare shear. You want to
Which one was that?
That's 0.
Guys, I told you guys. I told you explicitly that the triangle was going to be on. I pretty much said
Like,
you have to know how to use the triangle.
I use more circles for an answer, but the question asked for triangles. So,
That's right. It did.
so yeah.
It's not negative 0.2. It's going to be something different.
They can get the same answer for the one, right?
Okay, so.
Okay. Sorry, I shouldn't be like that.
Yeah.
I did. Yeah. Yeah.
What's, for the third one, what was the shear stress?
I'm trying to remember. That was I can't remember the answer.
Because I think I might have crossed out the right answer and then wrote a wrong one.
Okay.
Oh no.
Let me.
So yeah, so it's going to be. It's basically going to be double.
Here. That's what I got. I haven't checked this yet.
Yes! I think mine was positive. But it was the same number.
Okay. It should be negative. I'm just making sure that I did right. Because here's the thing with your professors, if they write their own exam questions, we have to double check that we got them right, right? So as the exams are coming in, this is what I do, I'll perfectly admit that. And I was like, oh, I made that little blip there, right? And so then it gets fixed. So it's nice when you have students in the class that are really good because you're like, okay, they agree with me.
Yeah, I originally was adding the 100 sine theta, whatever, with the 50 sine theta, whatever, and then I realized last second that didn't make sense. And so I made it a negative sign.
Yeah.
Well, also, my number was a little bit different though, because I was using 101,325 pascals instead of 101.2 kilopascals.
But why? It shouldn't have, because I gave you the hoop stress.
No, I mean for the conversion, I was using 101,325 instead of 101.3.
But I'm still confused for B. I gave you the hoop stress. I told you the hoop stress was 100 megapascals.
Yeah, but when I calculated the axial stress, I got like 50.6 because I was using.
But it's just divide this by 2.
Yeah.
I know, I didn't think.
No, like there's, so you went back and you like plugged it back in the, I'm confused.
I did PR over 2T again, but I used
Okay.
101,325 to calculate the pressure instead
All
of
right.
101.3.
That's one way to do it, right? Just the longitudinal one is just half of whatever the hoop is.
Yeah, I realized that a little too late.
It's okay. It's not. Yeah,
Actually, I think I still had 21.7. Like I think rounding it rounded out again. But.
Okay. Yeah. All right. So, So I haven't graded them yet, and but I will obviously. And I mean, what can I say? It was not. Imagine if you didn't have exam 2, right, to look at before you took that, like from the spring. Those guys. So if you look at from the spring, I mean, they say comparison is the thief of joy. Somebody says that, right? So their exam number 1 their exam number 1, I didn't think was going to be super hard, but they did really bad on it. Their exam number 2, they did much better, okay? But it was okay, right? So, they though didn't have the luxury of the exam number, like seeing exam number 2 in this form. And then this one was kind of a modified version of exam number 2 from the spring. Anyway, and then if you look back, I was not very kind, I don't think, back in 2015, 2016. Those exams were really brutal.
Just crush hopes and dreams.
Yeah, but yeah, no, thank you guys for sticking through it. I didn't think it was, these calculations are not trivial, right? They take some time, and there are lots of places where you can get hung up. Okay.
What's the class that's considered like after this? Like there's statics and then this. Like what's the one that's the same? Like,
So I would say design and mechanical components is kind of the one that's most relevant and kind of follows up on this closest. Because that's kind of design and mechanical components, you do a lot of review. And then one thing we don't cover in this class is fatigue. Okay, and fatigue is very relevant. You need, once again, you're looking at yield strength, ultimate tensile strength. You're looking at how things break, right? So, like I say, I feel at Rutgers, this is kind of like why things break 2, and then DMC is kind of why things break 3.
I also thought originally that I thought dynamics was like the follow up to statics because everyone was saying that. That's why it seems like when you get to dynamics, it's not even remotely similar.
No, and it's interesting that statics is a prereq for dynamics.
Yeah, it has nothing to do with it.
We got that on record. So,
That's very mechanical.
I mean, some of it is also. Yeah, some of it is also that. I mean, there are multiple things going on in terms of how you build a curricula, or how you build a curriculum, and if there were no prereqs in place, a lot of people would probably just try to load up as many credits as they could, and that can also be detrimental for people. But I can't justify. I mean, I think that feedback is good, and it's something that's in there.
Well, I also never understand why we go faster in physics. That, sometimes we do physics that outdoes the math we learned, or is correct with the math we learned. It doesn't make sense.
Uh-huh.
I don't get that.
Well, that's a fun thing about a lot of the courses in mechanical engineering is that
Is the principal?
we can usually teach the amount of math that you need as we're going, right? Because this class, none of the math is new. None of the math should be new to you.
This one plus that.
Although we did, but I guess we did talk briefly about eigenvectors, eigenvalues a little bit, but that's.
Well, everyone's taking.
Yeah, so, but we're not, that's not a required thing, it's more like for your information.
Well, it's more like a little minor part of it.
Yeah, and that's not how we solve the problems that are on exams.
But when we started doing differential equations in physics, before we started doing them in differential equations, I was like, in physics 2B.
Oh, yeah, when the Schrödinger's equation, you did all the different cubes.
Yeah, and you like hadn't done that yet in diffie-q. And then you get to that part in diffie-q and you're like, this is so much easier than I thought it was.
Yeah.
Really good.
Well, if you have suggestions, please feel free to send them to me. In my role as undergraduate director for the aerospace program, we are reviewing a lot of these things.
For aerospace, how do you get, I know you get a program in addition to your degree, how do you get that enroll in that program for a couple classes for aerospace, so I get that certificate?
So, if you're doing aerospace as a major, you can't get an aerospace certificate, right?
Oh, okay.
But if you're doing mechanical and you want to do aerospace certificate, yeah, then you fulfill the requirements as outlined, and then you get a certificate.
How do you have to apply for that, or do you just take the classes?
You just take the classes and make sure that the undergraduate, you probably want to make sure that the undergraduate director knows, but yeah. What we do, it actually doesn't show up on your transcript right now. But you will get a certificate, a literal certificate that comes in with your, a paper that comes in with your degree.
Is there a list of the requirements online? Because I looked up for the other programs. I only saw for the military one is the actual degrees. And
No. Yeah, we have it. You'll get the certificate if you go in the handbook. Yeah. If you have questions, send a message to Professor Zoe from Cambridge. If you have questions about aerospace, send them to me.
Why is mechanical and aerospace the same department? I feel like they're kind of different.
So this has been a trend. Okay, there used to be, so MIT has a separate mechanical and aerospace, Purdue has separate mechanical and aerospace, Illinois I think has separate, Austin has separate, Stanford has separate I think. But there was a lot of consolidation. Even some materials, like we have a separate material science and engineering from mechanical and aerospace, but even some of those have combined. So over the years, as opportunities change, as funding changes, as fields change, you've seen some mergers between departments. And then you've seen other departments spring up, like biomedical, right? That just kind of, when those biomedical and engineering departments sprung up, they were taking from different disciplines, right? They were taking from mechanical, from chem and bio, and then chemical, you're seeing, right? Chemical engineering departments, a lot of it's chem and bio, right? They changed their names to accommodate what's happening in the real world. Yeah. What's that?
That was based on my schedule.
It's the same time.
I was like, no.
No, because it's the 90, go on slides. It's
you use this one, you use this plus that.
Yeah, so this is
for 3
for the rectangular percent, and that other one is for the 60.
I tried that, just that, and I tried to divide by 2. I don't know if there's that first one.
It's just the same.
What happened?
Let me try.
That's what I wanted for my calculator. I just made these all.
You got-
this whole part equal to
You
0.
got
and
something
then-
right? Is that what you're excited about?
When I didn't.
But then you say not telling them?
Dude,
George, by the end of the semester, can I see you with a piece of paper or a pen or something writing down your work?
It on the exam, it hurts so much it's doing it.
Yeah, because they're how do you know? If you're studying, how do you go back and look at what you did to get the problems?
I just do it all.
Dude!
Dude! You're looking for, yeah.
okay, for your MAE degree, use paper. Alright, that's my request, because guess what, the exams are on something called paper. I mean, if you're gonna use, you don't have to, I love the tablet, right? So if you have a pen, okay, and if you do it in OneNote, that's fine, right? But
You know I have a pen.
if you don't have a pen and you're not, I think, paper is the moment to keep track of what's going on.
I have a sharp in my car.
Without using paper.
I have a black sharp in my car.
I don't know how you do that.
Something that has notebook so I can take off the tags.
I don't use paper.
Oh, is it off that?
You just
I have a
like,
black
this
sharp.
notebook has been with me, I think,
Oh.
since freshman year.
Okay, in this class, how can you draw the stress and the strain?
I mean.
You just imagine.
You just imagine it, huh? Okay, well, that's great.
Like more circle, it's a circle.
How do you do more circle?
I mean.
Take notes.
Okay.
Yeah.
So maybe, George, what I should say is, I'm gonna try teaching a class without using a pen or slides or paper. I just verbalize to you the equations. That would, that's great.
Can do that.
Thank you for writing your answers to the exam.
He was doing VR.
Huh?
He was doing like VR or something like
Yeah, VR. Yeah.
that. Or augmented reality, it's like.
Oh.
You see the power video where it's like has the augmented reality classes where it's like obviously it doesn't hinder your ability to see normal stuff, but like there's no dashboard, no nothing. It's all like it's like literally just open like extra open space.
To actually work well with your eyes.
Oh, you can force for augmented reality headsets. They spend like $50,000 helmet getting perfectly calibrated to the pilot's head.
So I don't understand how you can just have
cars,
cars
like some Bugatti or like high-end Ferrari type things, not like
you have to get them calibrated to your eyes.
Do you have any questions on the horse?
There's nothing on 3 for the question, but it's 3
For which one?
for 20, session 20.
Okay, yeah, we're running out of time.
Yeah.
We'll try to see what the question was. Yeah, for the absolute max shear strain, try it with the radius. And we're trying with the radius to treat in this as regular, so not divided by 2. And then we got wrong, we tried to divide by 2.
So remember, you gotta multiply this by 2, right? Because we're interested in this
Oh.
quantity, right? Like, so you have to do 2 times that.
Oh,
That's why it's a dumbass though.
is it supposed to be negative or something?
Yeah.
Oh, I have the square root around the wrong thing.
Okay.
That'll do it.
Yeah.
Yeah, but so again, right? Moore circle is your friend. All right, but okay.
Oh, by the way, I checked my answer on the exam would be 21.4 because it was 150.66 was what I was using.
Okay.
Is that gonna go back to haunt me?
No, I don't think so. I don't know. Don't quote me on that. Check your paper for the final answer.
Happy I got one question.
Dude, the middle one, like,
I know I did all of these steps for it, but
I'm just so apt to make little mistakes here and there that I don't think any of them are actual numbers. As I put the negative or positive,
Which
or
one?
that,
Zero X one.
It is 0.
like the hidden
The
out part.
next one is just
yeah.
the trend that was right.
Those the only ones.
Like, okay, I won the first
Epsilon
one.
is
So,
gonna be
As long as I was partial credits,
stress,
I got all within.
stress, actual stress, right? If you ever keep,
So I think I'll probably end up getting like.
right?
Yeah.
That could be, epsilon, you do that, so that would be.
You're so.
So, wait, but you have, this is a. Okay, sure. So
Bro, yesterday,
the
bro,
one has,
3-4 bottles just to sleep with.
stresses aren't the same, but quite
This guy's not drinking 3 bottles of tequila.
Oh, one line, okay.
Not
Okay, this is what I
Oh,
got.
yeah,
Yeah, but I'm trying to remember it.
No human is doing that. Steve Lewis is not trying that.
What you have to remember is that
Yeah, but he's not.
where you go, 3 bottles from 2 or that. That fits in, because the soft stress,
Because we don't do that.
right, it causes there to be less strain.
That.
Remember, it's 1 over E.
No, I don't trust it.
Okay, so,
Act on the thing. Remember that how he reads the street. Uses Z as a second.
Yeah, that's what I'm saying.
so, let's see, session, this is session 21.
Okay, how do we do for it? Cause it seems like there's a lot more information than we need. But I feel like.
Alright. So, for section 21, question 4, alright? What do we have? We have a cylindrical pressure vessel. Okay. And it says that we have an A rosette and a C rosette, right? So the A rosette is in the longitudinal. The C rosette is like that. Okay? So what we have, right, is the question of, we have a pressure P, we have, sigma H is equal to PR over T, right? And sigma L, we'll call it, is equal to PR over 2T, correct? Everyone agrees with these? Okay. So you saw for rectangular rosette, no, this is, I don't even have it up, hold on a sec. Okay, this is for the rectangular rosette, right? You see that we can figure out what epsilon B, epsilon C, epsilon A, what they all are, right? Now, we're interested, they're asking, what is epsilon B reading? Well, the gamma xy is going to be 0, okay? In this particular orientation that we're talking about, okay? At this particular element, right? With this coming out here and this coming out here, like that. So now we need to figure out what epsilon x and epsilon y are. Okay, so let's just write this out. Epsilon b is going to be 1/2 epsilon x plus epsilon y plus gamma xy, and we're saying that this one is 0. Okay, so now the question is, what are epsilon x and what are epsilon y? Let's just say that this is the x direction, and that this is like coming out where these are. The top, we'll say that's the y direction. Not exactly, I'm sorry, not coming out. Coming along, like, so along there, that's the y, or like along there, that's the y direction, right? So z is the radial direction, right? And then we have x and y. Well, what is epsilon? Let's say now that, so we're saying that the hoop stress, this is sigma y, and we're saying that this is sigma x. Okay. Now you tell me, what is epsilon x?
One over 8 times bracket sigma x minus new.
There we go. Yeah. That's right. Right? Remember this formula? Right? Because what's happening is that stress in the orthogonal directions takes away from the strain in the direction of interest. So we're saying that this one's 0. Okay? Epsilon y again, that's 0. Okay? Okay, so you have a Poisson ratio, right? You have an elastic modulus. So you can figure out what epsilon x and epsilon y are, and then you can plug them in and figure out what the strain should measure in B. Does that make sense?
Yes.
Okay. Questions? Because you all were looking at this one as well. Okay.
That's 10 and 9. So 201 E9. Or times 10 as power.
What's microstream? You have to multiply by 1,000?
Like 10 to 6.
Minus 6, or 10 to the 6 if you're in regular strain going there.
I fully thought my graph was done, I would be different units for like, not embarrassing about that.
I thought that's like a week, first week of class.
No, literally like half this course, I'm like, I'm so confused. I was like, I don't understand what this seems to be.
You know, the first time I cranked out, I was like, wait, is that my career or that what it is? But I think that is what
Throw that pussy.
Zero to also, let's start with type of 10. Well, you're fastest at it.
I still can't get 3.
So which one would be X? And yeah, what?
There's only 4 questions for this one, right? Okay, I can't get 3.
You multiply by 2, right?
Yeah, I'm like, yeah.
So that's right. If you're winning from random.
Yes.
Yeah.
Each more circle.
Is it minus or plus in the square?
Not more circles.
It's plus, right?
How much is that?
It's, here's the equation.
That's a little different.
It's X minus
So
one.
it should be 2 times.
Yeah.
2 times the whole thing. Yeah.
Basically, it's,
Well,
our first radius
it's
is
not.
gamma x y over 2.
It's.
Might be squared. And you,
Where?
radius is,
Right,
that's square
Yep.
plus.
Yeah, that's
So that's
over
what's
2.
right.
Get that. I had that before.
Gamma x y over 2 square, and also it's epsilon x minus epsilon y over 2 square.
What's the difference with this one?
The over 2 change.
So this should give you the right answer, right?
Yes.
A's are keys.
Oh, no.
Point is, it's
Oh,
well, no. That's the radius.
Everything's square, right?
I mean, the numbers are going to go over that already.
Over 2.
In the all three circles.
So that's what
Oh,
is
that's nice.
just 20.
Well, I was going this
No?
You like that one will give you the answer.
10,
Where else do you have to do it?
minus 6.
I mean, the whole thing, I does much do it. So,
6.
works.
5.
Once we do this, they could half a circle and you figure
Oh, so we
Well,
can calculate
it's
once.
half a circle
The
is
reason why this would be wrong.
I mean,
That's,
Right, perfect.
it's built into the whole circle, times 2 is your answer.
I think in your calculator, I think I might just use that, it's looking how efficient it is now.
Basically, it's find
Mr.
the,
What's up?
single one.
I don't see why.
So I will fix epsilon, put it in this case, but.
I don't see why this
Well, I
isn't
might
giving
do.
me the right answer. for question.
Okay, that's not this one, right?
If you
No.
multiply the radius by.
It's just the twice the radius, right?
Is it,
Which radius?
So,
this is the big circle,
let's see.
Yeah,
isn't it centered around the horizontal line?
yes, so, yeah, essentially, it's radius times 2 of the circle, you can find the radius, you have to figure it out.
Okay.
So for absolute max, right? You're using, are you defining your radius as the principal strain minus 0 over 2?
No.
That's why.
Oh.
So for number 3, is this session 22 or 20? Oh, this is 21. This is, yeah, because I'm confused. We're going back and forth.
Can I
Okay.
still use the square root of everything to make more circle to find the principal stress?
Yeah, so I mean, let's look at this question, right? This is session number 3, or session 21, question number 3. Okay, so in this case, right, you have a plane strain, or you have plane strain, but we have epsilon x equals some quantity, we have epsilon y equals some quantity, and we have a gamma xy, right? Okay, so how do we go about making the circle? You tell me.
We find the radius with ex minus ui over 2 squared plus gamma xy over 2 squared.
Tell me not in equations.
Oh, you
plot EX gamma XY and EY negative gamma XY,
Okay,
and then connect them with a line.
let's show me the order. So what do you do first?
EY negative gamma XY.
Okay, we can do it that way. All right, so that's going to give us a point out here.
And then the average strain, which would be
Yeah, like we can do it like this is not the best. Yeah, but that's fine. Yeah, so this is going to be the middle, right?
yeah.
Okay.
And then epsilon X negative gamma, I mean epsilon Y negative gamma XY.
Sure. Sure, like that. So that's up here, right? You don't have to do both, but we can.
Are your numbers similar to these?
You don't have to, you can just do one of them.
So all three of us could
Yes.
What do you do? What's your answer? That's 21. Add 21.6.
Right?
What we
Okay.
do is,
It's gamma xy over 2, by the way, right? So now this one is your principal strain, right?
there you go.
Okay, so the principal strain is going to be equal to, like you said, it's the average, right? And we have to figure out what this radius is, right? So this radius,
That's pretty close.
right? So let's do a couple things. So the radius, in this case, is going to be equal to the square root of epsilon x minus epsilon average squared, right?
not really.
Plus gamma xy over 2 squared. We agree with this? Okay, that's the radius. So then epsilon 1, this is going to be equal to the epsilon average, right? Plus r. We agree with that?
Yes.
Okay, that's how we get over here. Okay. And I guess epsilon, I didn't say what epsilon average is, but epsilon average, right, is the average of these two.
Yeah.
Okay, so we're good with that? Okay, so then what we had to do, right, is we have to come up with for the absolute maximum shear strain, right? What we have to do is we have to draw another Mohr circle, right? Like this. Okay? And so then this is becoming the dominant R max. Right? So the R max, right, is just epsilon 1 minus 0 over 2. Okay? And so that's nice, right? So but then the gamma xy max over 2 is equal to R max. So gamma xy max is equal to 2 R max. Okay. Okay, I think that's time. Thank you, everybody. Good luck. There's a lot to do this weekend with getting through the failure criteria. Okay? Please do it, though, because the final is a week from today.
It's Thursday, man.
It's Thursday. And then your summer will go without me. It'll be so sad.